JEP 446, Scoped Values, Preview. Summary: introduce scoped values, values that may be safely and efficiently shared to methods without using method parameters. They are preferred to thread local variables, especially when using large numbers of virtual threads. This is a preview API. In effect, a scoped value is an implicit method parameter. It is as if every method in a sequence of calls has an additional, invisible, parameter. None of the methods declare this parameter, and only the methods that have access to the scoped value object can access its value, the data. Scoped values make it possible to pass data securely from a caller to a faraway callee through a sequence of intermediate methods that do not declare a parameter for the data and have no access to the data. History: scoped values incubated in JDK 20 via JEP 429. In JDK 21 this feature is no longer incubating, instead, it is a preview API. Goals: 1. Ease of use. Provide a programming model to share data both within a thread and with child threads, so as to simplify reasoning about data flow. 2. Comprehensibility. Make the lifetime of shared data visible from the syntactic structure of code. 3. Robustness. Ensure that data shared by a caller can be retrieved only by legitimate callees. 4. Performance. Allow shared data to be immutable so as to allow sharing by a large number of threads, and to enable runtime optimizations. Non-goals. 1. It is not a goal to change the Java programming language. 2. It is not a goal to require migration away from thread local variables, or to deprecate the existing thread local API. Motivation: Java applications and libraries are structured as collections of classes which contain methods. These methods communicate through method calls. Most methods allow a caller to pass data to a method by passing them as parameters. When method A wants method B to do some work for it, it invokes B with the appropriate parameters, and B may pass some of those parameters to C, etc. B may have to include in its parameter list not only the things B directly needs but also the things B has to pass to C. For example, if B is going to set up and execute a database call, it might want a connection passed in, even if B is not going to use the connection directly. Most of the time this pass what your indirect callees need approach is the most effective and convenient way to share data. However, sometimes it is impractical to pass all the data that every indirect callee might need in the initial call. An example: it is a common pattern in large Java programs to transfer control from one component, a framework, to another, application code, and then back. For example, a web framework could accept incoming HTTP requests and then call an application handler to handle it. The application handler may then call the framework to read data to the database or to call some other HTTP service. At override: public void handle request response //user code called by framework var user info equals read user info. Private user info read user info, return, user info framework.read key user info, context, / call framework. The framework may wish to maintain a framework context object, containing the authenticated user ID, the transaction ID, etc., and associate it with the current transaction. All framework operations use the context object, but it's unused by, and irrelevant to, user code. In effect, the framework wishes to communicate its internal context from its serve method, which calls the user's handle method, to its read key method. 4. Framework.read key > use context. 3. Application.read user info. 2. Application.handle. 1. Framework.serve + create context. The simplest way to do this is by passing the object as an argument to all methods in the call chain. At override: void handle request response framework context var user info equals read user info context. Private user info read user info framework context return user info framework.read key user info context. There is no way for the user code to assist in the proper handling of the context object. At worst, it could interfere by mixing up contexts. At best, it is burdened with the need to add another parameter to all methods that may end up calling back into the framework. If the need to pass a context emerges during redesign of the framework, adding it requires not only the immediate clients, those user methods that directly call framework methods or those that are directly called by it, to change their signature, but all intermediate methods as well, even though the context is an internal implementation detail of the framework and user code should not interact with it. Thread local variables for sharing. Developers have traditionally used thread local variables, introduced in Java 1.2, to help share data between methods on the call stack without resorting to method arguments. A thread local variable is a variable of type thread local. Despite looking like an ordinary variable, a thread local variable has one current value per thread. The particular value that is used depends on which thread calls its get or set methods to read or write its value. Code in one thread automatically reads and writes its value, while code in another thread automatically reads and writes its own distinct instantiation. Typically, a thread local variable is declared as a final static field so it can easily be reached from different methods, and private so that it cannot be directly accessed by client, user, code. Here is an example of how the two framework methods, both running in the same request handling thread, can use a thread local variable to share a framework context. The framework declares a thread local variable, context, 1. When framework.serve is executed in a request handling thread, it writes a suitable framework context to the thread local variable, 2, then calls user code. If and when user code calls framework.readKey, that method reads the thread local variable, 3, to obtain the framework context of the request handling thread. Public class framework, private final application, public framework application app. This.application equals app. Private final static thread local framework context equals new thread local / 1. Void serve request response. var context equals create context request, context.set context, / 2, application.handle request, response. Public persisted object read key string key, var context equals context.get, / 3, var db equals get connection context, db.read key. Using a thread local variable avoids the need to pass a framework context as a method argument when the framework calls user code, and when user code calls a framework method back. The thread local variable serves as a hidden method argument, a thread that calls context.set in framework.serve and then context.get in framework.read key will automatically see its own local copy of the context variable. In effect, the thread local field serves as a key that is used to look up a framework context value for the current thread. While thread locals have a distinct instantiation in each thread, the value that is currently set in one thread can be automatically inherited by another thread that the current thread creates if the inheritable thread local class is used rather than the thread local class. Problems with thread local variables. Unfortunately, thread local variables have numerous design flaws that are impossible to avoid. 1. Unconstrained mutability. Every thread local variable is mutable. Any code that can call the get method of a thread local variable can call the set method of that variable at any time. This is still true even if an object in a thread local variable is immutable due to every one of its fields being declared final. The Thread Local API allows this in order to support a fully general model of communication, where data can flow in any direction between methods. This can lead to spaghetti-like data flow, and to programs in which it is hard to discern which method updates shared state and in what order. The more common need, shown in the example above, is a simple one-way transmission of data from one method to others. 2. Unbounded lifetime. Once a thread's copy of a thread local variable is set via the set method, the value, to which it was set, is retained for the lifetime of the thread, or until code in the thread calls the remove method. Unfortunately, developers often forget to call remove, so per thread data is often retained for longer than necessary. In particular, If a thread pool is used, the value of a thread local variable set in one task could, if not properly cleared, accidentally leak into an unrelated task, potentially leading to dangerous security vulnerabilities. In addition, for programs that rely on the unconstrained mutability of thread local variables, there may be no clear point at which it is safe for a thread to call remove. This can cause a long-term memory leak, since per-thread data will not be garbage collected until the thread exits. It would be better if the writing and reading of per-thread data occurred in a bounded period during execution of the thread, avoiding the possibility of leaks. 3. Expensive inheritance. The overhead of thread local variables may be worse when using large numbers of threads, because thread local variables of a parent thread can be inherited by child threads. A thread local variable is not, in fact, local to one thread. When a developer chooses to create a child thread that inherits thread local variables, the child thread has to allocate storage for every thread local variable previously written in the parent thread. This can add significant memory footprint. Child threads cannot share the storage used by the parent thread because the thread local API requires that changing a thread's copy of the thread local variable is not seen in other threads. This is unfortunate, because in practice child threads rarely call the set method on their inherited thread local variables, toward lightweight sharing. The problems of thread local variables have become more pressing with the availability of virtual threads, JEP 425. Virtual threads are lightweight threads implemented by the JDK. Many virtual threads share the same operating system thread, allowing for very large numbers of virtual threads. In addition to being plentiful, virtual threads are cheap enough to represent any concurrent unit of behavior. This means that a web framework can dedicate a new virtual thread to the task of handling a request and still be able to process thousands or millions of requests at once. In the ongoing example, the methods framework.serve, application.handle, and framework.readKey would all execute in a new virtual thread for each incoming request. It would be useful for these methods to be able to share data whether they execute in virtual threads or traditional platform threads. Because virtual threads are instances of thread, a virtual thread can have thread local variables. In fact, the short-lived non-pooled nature of virtual threads makes the problem of long-term memory leaks, mentioned above, less acute. Calling a thread local variables remove method is unnecessary when a thread terminates quickly, since termination automatically removes its thread local variables. However, if each of a million virtual threads has its own copy of thread local variables, the memory footprint may be significant. In summary, thread local variables have more complexity than is usually needed for sharing data, and significant costs that cannot be avoided. The Java platform should provide a way to maintain inheritable per-thread data for thousands or millions of virtual threads. If these per-thread variables were immutable, their data could be shared by child threads efficiently. Further, the lifetime of these per-thread variables should be bounded. Any data shared via a per-thread variable should become unusable once the method that initially shared the data is finished. Description: a scoped value allows data to be safely and efficiently shared between methods in a large program without resorting to method arguments. It is a variable of type scoped value. Typically, it is declared as a final static field so it can easily be reached from many methods. Like a thread local variable, a scoped value has multiple values associated with it, one per thread. The particular value that is used depends on which thread calls its methods. Unlike a thread local variable, a scoped value is written once, and is available only for a bounded period during execution of the thread. A scoped value is used as shown below. Some code calls scoped value.where, presenting a scoped value and the object to which it is to be bound. The call to run binds the scoped value, providing a copy that is specific to the current thread, and then executes the lambda expression passed as argument. During the lifetime of the run call, the lambda expression, or any method called directly or indirectly from that expression, can read the scoped value via the values get method. After the run method finishes, the binding is destroyed. Final static scoped value less than greater than v equals scoped value.new instance. / in some method. Scoped value where v, value, run, greater than, v.get, call methods. / in a method called directly or indirectly from the lambda expression, v.get. The structure of the code delineates the period of time when a thread can read its copy of a scoped value. This bounded lifetime greatly simplifies reasoning about thread behavior. The one-way transmission of data from caller to callees, both direct and indirect, is obvious at a glance. There is no set method that lets faraway code change the scoped value at any time. This also helps performance. Reading a scoped value with get is often as fast as reading a local variable, regardless of the stack distance between caller and callee. The meaning of scoped. The scope of a thing is the space in which it lives, the extent or range in which it can be used. For example, in the Java programming language, the scope of a variable declaration is the space within the program text where it is legal to refer to the variable with a simple name, JLS 6.3. This kind of scope is more accurately called lexical scope or static scope, since the space where the variable is in scope can be understood statically by looking for, and, characters in the program text. Another kind of scope is called dynamic scope. The dynamic scope of a thing refers to the parts of a program that can use the thing as the program executes. If method A calls method B, that, in turn, calls method C, the execution lifetime of C is contained within the execution of B, which is contained in that of A, even though the three methods are distinct code units. +-A +-B time +-C vertical bar underscore vertical bar underscore vertical bar underscore v. This is the concept to which scoped value appeals, because binding a scoped value v in a run method produces a value that is accessible by certain parts of the program as it executes, namely the methods invoked directly or indirectly by run. The unfolding execution of those methods defines a dynamic scope. The binding is in scope during the execution of those methods, and nowhere else. Web framework example with scoped values. The framework code shown earlier can easily be rewritten to use a scoped value instead of a thread local variable. At 1, the framework declares a scoped value instead of a thread local variable. At 2, the serve method calls scoped value.where and run instead of a thread local variable's set method. Class framework, private final static scoped value framework context equals scoped value.new instance //1 void serve request response var context equals create context request scoped value.where context //2 run greater than application.handle request response public persisted object read key string key var context equals context.get //3 var db equals get connection context db.read key. Together, where and run provide one-way sharing of data from the serve method to the read key method. The scoped value passed to where is bound to the corresponding object for the lifetime of the run call, so context.get in any method called from run will read that value. Accordingly, when framework.serve calls user code, and user code calls framework.read key, the value read from the scoped value, 3, is the value written by framework.serve earlier in the thread. The binding established by run is usable only in code called from run. If context.get appeared in framework.serve after the call to run, an exception would be thrown because context is no longer bound in the thread. As before, the framework relies on Java's access control to restrict access to its internal data. The context field has private access, which allows the framework to share information internally between its two methods. That information is inaccessible to, and hidden from user code. We say that the scoped value object is a capability object that gives code with permissions to access it the ability to bind or read the value. Often the scoped value will have private access, but sometimes it may have protected or package access to allow multiple cooperating classes to read and bind the value. Rebinding scoped values. That scoped values have no set method means that a caller can use a scoped value to reliably communicate a constant value to its callees in the same thread. However, there are occasions when one of the callees might need to use the same scoped value to communicate a different value to its own callees. The Scoped Value API allows a new nested binding to be established for subsequent calls. Private static final scoped value string x equals scoped value.new instance. Void foo scoped value.where x hello run greater than bar. Void bar system.out.println x.get / prints hello. Scoped value.where x goodbye run greater than baz system.out.println x.get / prints hello. Void baz system.out.println x.get / prints goodbye. Bar reads the value of x to be hello, as that is the binding in the scope established in foo. But then bar establishes a nested scope to run baz where x is bound to goodbye. Notice how the goodbye binding is in effect only inside the nested scope. Once baz returns, bar sees the hello binding. The body of bar cannot change the binding seen by that method itself but can change the binding seen by its callees. This guarantees a bounded lifetime for sharing of the new value. Inheriting scoped values. The web framework example dedicates a thread to handling each request, so the same thread executes some framework code, then user code from the application developer, then more framework code to access the database. However, user code can exploit the lightweight nature of virtual threads by creating its own virtual threads and running its own code in them. These virtual threads will be child threads of the request handling thread. Context data shared by a code running in the request handling thread needs to be available to code running in child threads. Otherwise, when user code running in a child thread calls a framework method, it will be unable to access the framework context created by the framework code running in the request handling thread. To enable cross-thread sharing, scoped values can be inherited by child threads. The preferred mechanism for user code to create virtual threads is the Structured Concurrency API, JEP 428, specifically the class Structured Task Scope. Scoped values in the parent thread are automatically inherited by child threads created with Structured Task Scope. Code in a child thread can use bindings established for a scoped value in the parent thread with minimal overhead. Unlike with thread local variables, there is no copying of a parent thread's scoped value bindings to the child thread. Here is an example of scoped value inheritance occurring behind the scenes in user code. The server.serve method binds context and calls application.handle just as before. However, the user code in application.handle calls run the read user info and fetch offers methods concurrently, each in its own virtual threads, using structured task scope.fork, 1, 2. Each method may use framework.read key which, as before, consults the scoped value context, 4. Further details of the user code are not discussed here, see JEP 428 for further information. At override. Public response handle request response, try, var scope equals new structured task scope.shutdown on failure. Supplier user info user equals scope.fork, greater than read user info, // 1, supplier list offer offers equals scope.fork, greater than fetch offers, // 2, scope.join. Throw if failed, // wait for both forks. Return new response user.get, order.get, catch, exception x, report error response, x. Structured task scope.fork ensures that the binding of the scoped value context made in the request handling thread, in framework.serve, is read by context.get in the child thread. The following diagram shows how the dynamic scope of the binding is extended to all methods executed in the child thread. Thread 1 Thread 2, 5. Framework.read key > context. 4. Application.read user info, 3. Structured task scope.fork, 2. Application.handle, 1. Server.serve plus. The fork/join model offered by structured task scope means that the dynamic scope of the binding is still bounded by the lifetime of the call to scoped value.where run. The principal will remain in scope while the child thread is running, and scope.join ensures that child threads terminate before run can return, destroying the binding. This avoids the problem of unbounded lifetimes seen when using thread local variables. Legacy thread management classes such as fork-join-pool do not support inheritance of scoped values because they cannot guarantee that a child thread forked from some parent thread scope will exit before the parent leaves that scope. Migrating to scoped values. Scoped values are likely to be useful and preferable in many scenarios where thread local variables are used today. Beyond serving as hidden method arguments, scoped values may assist with 1. Re-entrant code. Sometimes it is desirable to detect recursion, perhaps because a framework is not re-entrant or because recursion must be limited in some way. A scoped value provides a way to do this. Set it up as usual, with scoped value.where and run, and then deep in the call stack, call scoped value. Is bound to check if it has a binding for the current thread. More elaborately, the scoped value can model a recursion counter by being repeatedly rebound. 2. Nested transactions. Detecting recursion can also be useful in the case of flattened transactions. Any transaction started while a transaction is in progress becomes part of the outermost transaction. 3. Graphics contexts. Another example occurs in graphics, where there is often a drawing context to be shared between parts of the program. Scoped values, because of their automatic cleanup and re-entrancy, are better suited to this than thread local variables. In general, we advise migration to scoped values when the purpose of a thread local variable aligns with the goal of a scoped value, one-way transmission of unchanging data. If a codebase uses thread local variables in a two-way fashion, where a callee deep in the call stack transmits data to a faraway caller via thread local.set, or in a completely unstructured fashion, then migration is not an option. There are a few scenarios that favor thread local variables. An example is caching objects that are expensive to create and use, such as instances of java.text.date format. Notoriously, a date format object is mutable, so it cannot be shared between threads without synchronization. Giving each thread its own date format object, via a thread local variable that persists for the lifetime of the thread, is often a practical approach. Alternatives. It is possible to emulate many of the features of scoped values with thread local variables, albeit at some cost in memory footprint, security, and performance. We experimented with a modified version of thread local that supports some of the characteristics of scoped values. However, carrying the additional baggage of thread local variables results in an implementation that is unduly burdensome, or an API that returns unsupported operation exception for much of its core functionality, or both. It is better, therefore, not to modify thread local but to introduce scoped values as an entirely separate concept. Scoped values were inspired by the way that many Lisp dialects provide support for dynamically scoped free variables, in particular, how such variables behave in a deep-bound, multi-threaded runtime such as interLispD. Scoped values improve on Lisp's free variables by adding type safety, immutability, encapsulation, and efficient access within and across threads.